Hello, I'm Ishani Janveja and I'm here to present InSight, a system for monitoring the state of the driver in low light using smartphones. Road safety is a major public health issue across the globe, with about two-thirds of the accidents occurring during nighttime or in low light conditions, and driver fatigue and distraction are the leading causes in such scenarios. We believe that the way to address this issue is by monitoring driver behavior and providing actionable feedback. In this work, we focus on developing a vision-based system such as the one shown in the figure, where we simply mount a smartphone in the vehicle for monitoring drivers' actions. However, monitoring in low light conditions using standard smartphones poses several challenges. The first one is that RGB frames captured by the smartphone lack information. For instance, in the image on the right, we can hardly see anything, let alone monitoring the driver's behavior. The solution for this is to use IR or FLIR cameras, but this requires additional camera support, thus making it an expensive and intrusive solution and hence not scalable. The second challenge is that pre-trained models for face and landmark detection do not work on low light images simply because they are trained on images taken in good lighting. For example, using a pre-trained model, we were able to detect faces in only 1% of 1,000 low-light images from a real-world drive. So how do we counter these issues? In our solution, we retrofit existing smartphones with a near-infrared LED, as shown in the image, to capture drivers' actions in low light. Unlike existing solutions, we repurpose the smartphone camera to capture NIR imagery, making the system low cost and also non-intrusive. So, can we use smartphones to capture NIR imagery? The short answer is yes. Typically, cameras are manufactured by placing IR filters in front of the light sensors, thus blocking the infrared spectrum shown in the gray region. However, in case of smartphones, which are mass manufactured and often the aim is to push costs low, the IR filters do not completely block out the near-infrared spectrum as shown by the pink region. This provides us with an opportunity to use smartphones to see in NIR light. Now, what kind of NIR LEDs can be used effectively with smartphones? As you see in the images captured by the smartphone, when we use LEDs with wavelength close to that of visible spectrum, more red color is visible, making the system intrusive. However, the filter blocks out most of the light on the other end of the NIR spectrum. Thus, we choose the 810 nanometer LED, which provides sufficient illumination. Another point of consideration is the intensity of the NIR LED, which is proportional to the power consumption. We used LEDs with 1.8 watt to illuminate the driver's face, which is typically at a distance of 40 to 50 centimeters. Now that we have NIR images captured using smartphone, our goal is to first detect the driver's face and localize facial landmarks, then use it to monitor driver fatigue based on eye blinks and yawns, and lastly, to measure attentiveness based on driver's gaze. In order to train our facial models, we first need to generate label data. However, labeling 68 facial landmarks manually on all training images would be laborious and also infeasible. Since IR imagery is much more effective in low light and can be used to extract labels, we leverage this insight and capture IR and NIR images in tandem using the setup shown on left. We then translate labels from IR images to images captured by the smartphone in NIR illumination. This is done using Homography Transformation. To demonstrate this process, we have an IR image which needs to be processed to remove the radial distortion due to the fisheye camera lens. We then detect landmarks on this image using standard models. And finally, the homography transformation matrix lets us map the landmarks to the corresponding NIR image captured using smartphone. We use this label data to train our models. To evaluate our system, we collected a dataset of driving videos across 15 drivers, some of it in the basement and rest on road for real-world scenarios. Our face detector trained on NIR images gives an accuracy of 90% and the landmark predictor gives a normalized root mean square error of less than 0.08, which is well within the acceptable error. Next, We have the results for blink detection and yawn detection on the basement data with 150 blink events and 180 yawn events. The F1 scores for detection of both these events is around 85%, showcasing the effectiveness of our NIR imagery-based models. We also demonstrate here our evaluation on real road data for mirror scanning. In this graph, you see the percentage of time when a driver scans the left or right car mirror at least once in a window of t seconds. We see a general trend of decrease in adherence to this rule from evening time to night time. To summarize, we presented InSight, an accurate, low-cost and non-intrusive system to continuously monitor the state of the driver in low light. Our system relies on NIR illumination, which is not visible to the human eyes but can be captured effectively by smartphones. We conduct a rigorous evaluation of the system in different settings. Further, we also present an alternative approach based on synthesizing thermal images using GANs for monitoring in low light. For more details, please read our paper. Thank you.